So continuing with significant figures, the take-home part is really that there's a limit to how well we know data that we collect with almost any instrument, and that limit might be that the instrument doesn't work, our technique might have sort of limited precision, we can't see the markings on a container, etc. So from the start, when we collect data, what we need to recognize is that we typically have, or not even typically, always have a numeric value, we have units, and the issue of SigFigs is about this last one, the implied uncertainty. So for example, we might measure the mass of something. So the mass of a penny, for example, we weigh on a triple beam balance and we see that it's 2.23 grams. So most students in lab very quickly get the rules that we write the number down. That's the main focus, I think, to start. And with a little bit of reminders, get grams down. And the uncertainty part is the lost. So when I survey the classes, typically most people have now taken statistics. So in that, you've talked about uncertainty or maybe standard deviation specifically. So there are quantitative ways that can be a fair bit of work to describe how well we know numbers. We rarely go that far in beginning chemistry classes. Instead, what we do is we have a convention, which is just sort of a simplification we all agree on, that says that when we write a number down, we have two of the digits, or not two necessarily, but all but the last digit, which we consider certain, meaning we know them. And then we have one more digit, which we're not 100% sure what it is numerically, but we think it still has some value. So in this case, we're saying that the 100th place, occupied by the 3 here, might be a 3, maybe it's a 2, maybe it's a 4, but it's not a 6 or a 7. So this code applied with our convention is that we're pretty sure, without quantifying that, but we're pretty sure that the value is actually between the 2.23 minus 0.01, so that'd be 2.22, and 2.23 plus the 0.1, or 2.24. So the way we write things and the way we again have this convention is that the uncertainty is plus or minus 1 of whatever the place is of that last digit. And again, that is a convention. If we were really careful and did the experiment 1,000 times, maybe we find that it's really plus or minus 0.023 grams, and we could say what the range is there. But again, the point here is we don't really want to get that bogged down in the discussion. We just want to say, hey, our rule is that the last digit we're not 100% sure of, but at the same time it's not just a number that I had to write down to meet some requirement that the class or the teacher imposed on it. Okay, so again, when you record data, it's always important to write the value and the units, and then we have this extra piece of information which is sort of coded in, which is how well we know something. Usually when we're recording things, we record all the digits that are possible, say on a balance, analytical balance when we're weighing things. But when we do calculations is where maybe things get a little more important. So if we were to look at calculations using SigFigs, kind of a point that I tell people to remember is that addition and subtraction are different and treated differently than multiplication and division. Okay, so first thing is just know that they're different, and we'll work on what those differences are. So one thing that is sort of an interesting consideration is that when we do addition and subtraction, the units of the numbers that we're handling have to be the same, right? I can add grams of one thing to grams of another, but I can't add grams of one thing to seconds, right? That would be meaningless. With multiplication and division, anything goes. I can multiply distance times time. I can take volume, divide it by mass, or vice versa. So I can combine things at different units, and I can combine things at the same units. If I multiply a distance times another distance, I get an area. Inches times inches gives me square inches. Okay, so what does that mean? There's a couple of ways to look at this, but if we do by example, let's just say I have two objects that I'm going to add together. One of them is 2.32 grams, and the other one is going to be 0.13 grams. Okay, and if I add those together, well, this may be a trivial example, but we'll do it anyway. I'm going to get 2.45 grams. Okay, if we look at what we mean by uncertain digits, this digit we claim, or rather this first number we said was an uncertainty of about 1/100th, so that 100th place where the 2 is uncertain. Likewise, the 100th place here is uncertain. So we might say, oh, well, if each of these is uncertain by 1/100th, maybe down here this is uncertain by 0.02. That would be assuming that the errors don't really cancel, or at least statistically don't. But what you'll see here is that they're the same magnitude. This is 100th, this is 2/100th. So it's the 100th place that is uncertain. So what that kind of suggests going backward is the way that this number is written is proper. If we looked at something maybe a little more interesting, if that's the right word. Before I move on, note too that this has 3 SigFigs, this has 2 SigFigs, and my answer here has 3 SigFigs by that description. If I do another quick example and say I have 112 pounds, and to that I add 0.21 pounds, and I do the math here, I'm going to say, okay, 112.21 pounds. First one I have 3 SigFigs, the 0.21 I have 2 SigFigs. My answer as written looks like 5, so what's the correct way to write it? And if I go back and look at this uncertainty here, this 112 suggests plus or minus 1 pound. This 0.21 suggests plus or minus 0.01 pounds. So if I add those guys together, 1 plus 0.01 is plus or minus 1.01 pounds. So that's telling me that the uncertainty is in this place, in the ones place here, and so my answer should be rounded to that. Okay, so the rule here is what we're doing. Do I have another colored pen somewhere? What we're doing is we're looking at the place, and the place that is least precise dictates what the answer should be written to. So up here, they were both the same precision, so we care about the 100th place. Down here, the least certain one, or the least precise in terms of magnitude, this plus or minus 1 pound versus plus or minus 100th of a pound, is the ones place, and so my answer should be rounded to the ones place. So again, with addition subtraction, the whole thing is about place. Right, and by place we mean the ones, or the tenths, or the hundredths place, whatever it might be, and whichever term in your calculation has the least precision dictates what the precision of the answer is. Okay, multiplication division, a little bit different. If I have, we'll do everything in distance for now, but if I have 0.20 times 2.35, starting using calculators for this, and let's see, these are both inches, so I'll be proper and say I'm using units everywhere. This is going to be numerically, what's that, 0.470 on my calculator. I'll say the zeros there. And the question is, well, how many SigFigs should I have here? And so Here, because, well, in this example, the units are the same, so I guess I'll need to do one with different units. But here, where I have something that's going to be precise to the hundredths place, again, something to the hundredths place, well, if I come down to this, is it proper that I be to the hundredths place here? And in fact, in this one it is, though for a different reason. When we do this calculation, really what we want to pay attention to is the uncertainty in relative terms. So rather than absolute plus or minus over here 1 gram, or down here the plus or minus the pounds, here I should be talking about percent. So 1 part, plus or minus 0.01 out of 0.20 is about a 5% error. 1 part here out of 2.35, so the hundredth place out of 2.35 would be roughly 0.5%. So this uncertainty is about a 5% error. Okay, it happens that it would be 0.01 inches, but we'll come back to this percentage more in another example. And so that's, I'll just finish this off. This guy's plus or minus 0.5%. You can check that with a calculator if you want. Because this one is sort of the weakest link with that 5% error, it sort of says that the answer should have the plus or minus a 5% error. And 5% of 0.47, what's that going to be? 5%, 0.05, 1% would be 0.5, so it'd be like 0.025, I think. I should really get a calculator out, make sure I can do a little bit of arithmetic here. So 0.05 times 0.47, so yeah, it's 0.0235. So the uncertainty here would be about, again, 0.02. That digit's uncertain, and so this should be written then as rounded to the hundredth place. Now the difference, and we'll come back to this with a better example, is that the reason this has 2 SigFigs is because this had 2 SigFigs more than what the place is. So if we do another example, I'll do something maybe with a ratio. Let's do speed. So if we said 5.0 meters divided by 0.002 seconds, and I do that calculation, let's see, 5 divided by 0.02, my mental math skills aren't working today. And so I'm going to get 2,500 meters per second. Alright, so here, this uncertainty of plus or minus a tenth of a meter would represent how much? Tenth of a meter, 1 in 50 would be about a 2% uncertainty there. This one, if we said plus or minus 0.001 seconds, that would be a 50% error here, or 50% uncertainty. It's not really an error. And so my answer really is going to be controlled by that. So plus or minus 50% here means this guy would range from like 1,200 to 5,000. And so suddenly this guy is going to be important, and so properly I'd want to round that guy to 3,000 meters per second. That squeezes in there. So the take home here is that we care, for shorthand, is how many SigFigs there are. So I had 2 SigFigs here. I had 3 SigFigs on this one. I've lost all my red pens. Is it a different color? Not really. Anyway, 2 SigFigs there, 3 SigFigs there. So this 2 being less than the 3 gave me 2 SigFigs here. Down here, I have 1 SigFig. Up here I had 2 SigFigs. So the 1 SigFig dictates the answer here. So addition, subtraction, we cared about place. Multiplication, division, we actually care about SigFigs. I replace up top there. I should write SigFigs up top here too, but no enough space. SigFigs. And very succinctly, the term with the lowest number of SigFigs dictates the SigFigs that are in the answer. So 1 SigFig is important, 2 SigFigs versus 3 was important there. A lot of times it'll work out to be the same. You know, this first example I had, I guess that one didn't because I had 2 SigFigs in my second term. Anyway, sometimes you will not appreciate the correct use of the calculation, and yet you still get the right answer because coincidentally the least precise number also had the least number of SigFigs. So there you go. But anyway, as you look at this and sort of contemplate it, to me the issue is that these guys are different. And so if there is a need to be careful with SigFigs that are in calculations, to me the important step is just reflecting on, hey, addition's different than multiplication, and hopefully that triggers what the thing is. I would say in most chemistry calculations, you know, the overwhelming majority of our calculations involve multiplication type things. You know, I'll just make up numbers here, but 90% of the time we care about multiplication division, so the SigFigs are what are important. And again, just making up numbers, 10% of the time we care about SigFigs in addition subtraction. Okay, hopefully that wasn't too sloppy and confusing, but there you have it. So SigFigs, it's a slightly lazy way of making sure that we've recognized the limits to how well we know things, but certainly it is not the end all. Okay.